Hey guys, so in today's video we're going to have a look at indices and index laws and a bit of an explanation behind them. So first, to start off with a bit of a background refresh, in mathematics, if we take a number, let's say 2, and we multiply it by itself multiple times, we know that we can represent this as, in this case, 2 to the power of 3. And when we do this, we refer to this bottom number as the base of the number, and this top part, which sometimes you'll hear referred to as the power, we'll refer to it as the index. And this holds true for any number. Let's say we take a number a, we multiply it by itself some number of times, we can represent this as a to the power of m, where m is the number of times. So, and this can be equal to 0, 1, 2, 3, etc. So there are a series of laws which dictate what happens to this index when multiplying, dividing, subtracting, or adding, or some other functions as well, when we manipulate different numbers or different bases of different indices. So let's have a look at each of these laws, and we'll do a brief example. Then in the next video, we'll go over a few more complex examples, some of which will require the use of multiple index laws to solve. So the first law which we'll look at says that a to the power of m times a to the power of n equals a to the m plus n. So let's say we have a number, 2 to the power of 4 for example, and we want to multiply it by 2 to the power of 2. So we know we can represent 2 to the 4 as 2 times 2 times 2 times 2, and 2 to the power of 2 as 2 times 2. And in this case, we're multiplying them together. So you can see where this law comes from and how we get the resultant 2 to the power of 4 plus 2. Which in this case gives us 2 to the power of 6, which you can see we sort of derived at the top here. So that's the first law and how it sort of makes sense. Let's have a look at the second law now. The next law says that a to the power of m divided by a to the power of n equals a to the power of m minus n. And this is kind of the inverse of the first law. Let's have a look at an example. 2 to the power of 3 divided by 2 to the power of 2. So we know we can represent this as 2 times 2 times 2 times, or 2 times 2 times 2 over, or divided by 2 times 2. And as we usually do when dividing numbers, we can cross out the same number on the top and the bottom. So if we do that in this case, we're just left with 2 in the numerator, or 2 to the power of 1, which is 2. Or if we are to apply the law, you'll see this is the same as 2 to the power of 3 minus 2, which equals 2 to the power of 1, which of course equals 2. So that's how that one's derived. Let's have a look at the next one now, which is a little bit different. It says that a to the m, all raised to the power of n, equals a to the m times n. So this one maybe will seem a little bit more unfamiliar. Let's have a look at another example, 2 to the power of 3, all raised to the power of 2. So here, if we were to represent 2 to the power of 3 as 2 times 2 times 2, and we to raise this to the power of 2, we know that when we raise a number to the power of 2, we multiply it by itself. So in this case, we'll end up with 2 times 2 times 2, all multiplied by 2 times 2 times 2. And you can quickly see where this comes from, that this is the same thing if we were to get rid of the parentheses as 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the power of 6, as we would have seen previously as well. And from our index law, that's the same thing as 2 to the power of 3 times 2 equals 2 to the power of 6. So that's where that one comes from. The fourth law is a little bit different once again. It says that a to the power of 0 equals 1. So this basically says that any number raised to the power of 0 equals 1. So let's have a look why this might be the case. Once again, let's take 2 to the power of 3 divided by 2 to the power of 3. And if we were to expand each of these again, 2 times 2 times 2 over 2 times 2 times 2, and cross everything out, you'll see it's the top on the same and the bottom. We're left with 1, because we have the same in the numerator and the denominator. And if we are to apply this formula, or apply our second index law, we'll end up with 2 to the power of 3 minus 3, which results in 2 to the 0, which equals 1, which we've worked out at the top. So that's why any number to the power of 0 equals 1. And the last index law, which is important, is a to the power of negative m equals 1 over a to the m. So basically this law says that if you have a negative value in the indice, that you can move that number to the denominator of the fraction where 1 is in the numerator. So let's have a look at how that sort of comes to be. If we have another number, 2 to the power of 2 divided by 2 to the power of 5 in this case, we can represent this same as we've been doing before. 2 times 2 in the numerator, 2 times 2 times 2 times 2 times 2 5 times in the denominator. And by crossing out terms, you'll see we're left with 1 over 2 times 2 times 2, which we can represent the denominator as 2 to the 3. And if we're to look at this same equation using our second index law, we're left with 2 to the power of 2 minus 5, which means we're left with 2 to the negative 3, because 2 minus 5 is negative 3. And you can see that these two terms are the same, therefore this equals 1 over 2 to the 3 as well. And that's why this last index law holds true. So those are the 5 main index laws and sort of how they came to be or why they exist. So in the next video, we'll have a look at solving some more complex equations using a combination of different index laws, sometimes multiple, and we'll also have a look at some faster techniques for solving some equations using indices. So thank you very much for watching. Leave any questions you'd like assistance with in the comments below. Thank you. Bye.